Physics in the Flesh, welcome to video 111, Law of Conservation of Energy 1. You drop a ball from a height of 1.8 meters and it bounces back to a height of 1.4 meters. A. What fraction of its initial energy is lost during the bounce? B. What is the ball's speed just as it leaves the ground after the bounce? And C. Where did the energy go? Okay, so we're going to start off this problem by drawing one of our handy pictures. Okay, so draw something really simple. You've got a ball and it's falling towards the ground. Okay, so this is falling downwards and it's going to cover a certain height. Okay, now, in the question, we're given a pretty good piece of information. Okay, the ball is dropped. Okay, so V1 is 0 at this point. And we're told that it's dropped from a height of 1.8 meters. Okay, so this height up here, so we'll call that H1 is equal to 1.8 meters. Okay, the ball falls down and then it bounces back up to a height of about 1.4 meters. Okay, so there's our second marker. H2 is 1.4 meters. Now, what fraction of its initial energy is lost during the bounce? Okay, so that's actually really simple to calculate. I mean, think about it like this. We only have two types of energy here, gravitational and kinetic, right? It has a certain height above the ground and it has a certain speed. So to figure out how much energy is lost, well, look at this. 0.4 meters of height is lost, and that has to do with the gravitational potential, also contributing to the total. So if you take the amount of height lost, which is 0.4 meters, and you divide it by the initial height that it was originally able to undergo, 1.8 meters, you get 0.22. Okay, so in other words, 22% of the energy is lost. And this is normal. We'll look at why the energy is lost in part C. But there's the answer to part A, 22% is lost. Okay, so for part B, what is the ball's speed just as it leaves the ground? So we actually don't have something to represent that on our picture, so let's do that. Just as it leaves the ground, that's right here. Okay, so we want to know the speed, V3, and at that point 3, our height, H3, is 0, right? We'll call this height down here 0, right there at the reference line. Okay, so because I'm looking for V3, I want to do my conservation of energy expression. Usually I like to have what I'm isolating for to be on the left of the equal sign. So I'm going to write ET3 equals ET1. Okay, so up to this point, the videos we've done are always ET1 equals ET2. In this case, you can use any 2 points. ET3 equals ET1. What I'm looking for is in this expression, so I keep it on the left. But it really doesn't matter. You can always isolate it later on. Okay, so just like in the previous problems, we're dealing with kinetic and we're dealing with gravitational potential. So we're going to do EG3 plus EK3 equals EG1 plus EK1. Okay, write the expressions down. So mgh3 plus 1 half mv3 squared equals mgh1 plus 1 half mv1 squared. Okay, so let's simplify this now. Mass appears in every term. It can disappear. We also know that V1 is 0, right? Because it's dropped. So V1 is 0. This entire thing disappears. And we're left with a nice expression. GH3 plus 1 half V3 squared equals GH1. And what we're looking for here is V3. Okay, so go ahead and bring the GH3 to the right. Well, you know what? We can actually cancel something else out, can't we? The H3 is 0. So why don't we cancel that out as well? Okay, that just made things even easier. Okay, so now to isolate for V3, we just simply multiply both sides by 2 and take the square root of the entire expression. So V3 is root 2GH1. Okay, plug in your values. The easy part. 2 times 9.8 meters per second squared times H1. H1 is 1.8 meters. Plug that in your calculator. When you crunch those numbers, you're going to get V3 is 5.9 meters per second. So that is the speed just as it leaves the ground right there. Obviously, when it gets to point 2, the speed's going to be 0 because it turns around, comes back down. Okay, so there's the answer to part B. And finally, part C, where does the energy go? Okay, so just think about this logically. If you're sitting down and someone behind you has a ball and they drop it, you're going to know that they have it because the ball makes a sound once it impacts the ground, right? Prior to that, you have no inkling that they're holding something in their hand. So yeah, part of the energy becomes sound and the other part of the energy becomes heat because as it impacts that ground, the amount of force that it impacts the particles with, it's going to have some heat left over. There's a little bit of friction there, you could say. Okay, so the idea is this, the energy becomes heat and sound. That's where the rest of the energy goes, right? Anyways, guys, I hope you enjoyed the video. That's it for this problem. If you liked it, be sure to smash that like button and stay tuned tomorrow for video 112, Law of Conservation of Energy 2. Hey guys, that's it for this episode. If you enjoyed it, be sure to check out some of my most recent videos posted over there on the right, which you can click on your screen right now and watch. Other than that, guys, I hope you enjoy the rest of your day, and I will catch you in the next video. Is the end screen too long this time? Wait, you're still recording? No! Oh. Gotta move that chair out of the way next time.